Welcome back, children. Welcome back to the lecture series on remote sensing and in our topic of resolution. Previously, we talked about three different types of resolution. Those resolution are visual resolution, spectral resolution, and radiometric resolution. In today's topic, in this particular lecture video, we will talk about temporal resolution. Now, before going into detail on temporal resolution, let's say what the word temporal means. Okay, so the word temporal here stands for time. So it is nothing but the time, and the resolution is the time difference. Okay, so we are going to talk about the different type of satellite time differences it take to collect the data, to sample the data, to operate the data. Okay, so let's begin our today's topic on temporal resolution. Temporal resolution describes the number of times an object is sampled or how often the data are obtained for the same area. Once again, I'm repeating it, that temporal resolution describes the number of times an object is sampled. Or you can also say that temporal resolution describes the number of times the data is been obtained for the same area. It has to be mentioned. Okay, if it is for different area, you can't say it is a temporal resolution of a satellite. It should be over the same area. In other words, you can say how number of time you pass from a particular object. Okay. For example, in general case, if you want to understand a temporal resolution, it's like your attendance system. It indicates that how many times you have attended the class, the same class. Okay. So it depends on your your attendance says that how many times the number of lectures you have attended is more. Let's say you are at a finer temporal resolution, or your attendance is good. So moving further, the absolute temporal resolution of a remote sensing image, remote sensing system to image the same area at the same viewing angle a second time is equal to the repeat cycle of a satellite. So here it is nothing but the definition of the repeat cycle, which I have already mentioned earlier. So if you remember, that repeat cycle is nothing but uh, the time taken by the satellite, okay, to pass through the same area at the same viewing angle the second time is considered as a repeat cycle. The repeat cycle of a near polar orbiting satellite is usually several days. For example, IRS-1C Resource-Set 2. These are the satellite which has a temporal resolution of Mensa cycle, repeat cycle of 24 days. Okay. You can take another example of Landsat, which has 18 days of repeat cycle. However, due to off-nadir viewing capabilities of the sensor and the side lobe of satellite path in adjacent orbits, the actual revisit period is in general less compared to the repeat cycle. So we actually say that the actual uh, temporal resolution of the data or your image depends on a variety of factors. As I've already mentioned, it depends on the capability of the satellite, the capability of the sensor, the swath overlap of the sensor, and the latitude or location. Because of some degree of overlapping in the imagining swath of the adjacent orbit is possible, more frequent imagining of some area is possible. So how I'm going to explain it? As you can see here in this particular image, this is a schematic of typical near polar satellite orbit. I'm talking about near polar satellite, and you can clearly see here that the side lapse increases with latitude. Okay, as the latitude increases, the side lapse increases, and towards the polar region, satellite orbits come closer to each other compared to the equatorial region. As you can see here, as the latitude increases, okay, the side lapse increases, and when it reaches to the polar region, it comes very near. This is just a schematic representation, just for an understanding that due to the structure of the surface, earth surface, this type of side lap and overlap frequent imagining possible, and it is different for different area. So when you talk about polar region, its temporal resolution is much higher compared to equatorial region. Okay, so polar region, as you move towards the latitude, the higher the latitude value, changes will occur in the same manner. Therefore, the polar region, the side lap is more, and therefore the more frequent images are available for polar region. Another image which would be helpful on understanding is this. So as you can see that in polar region, this is a particular image of a typical near polar satellite, and I have taken it from NRChem, Earth Sciences Department, available online, and you can clearly see that over the equator, you can see over the equator there is a huge difference between the cycles. There is no cycles, but when you move toward the polar region, here, the amount of area covered, the frequency of imagining the same area is more, mainly due to the side labs. Too many labs happening as you move towards here. In the similar way, as you move towards your number of images captured. In addition to the side lab, more frequent imagining of any particular area of interest is achieved in some of the satellite by pointing their sensor, okay, uh, to image the area of interest between different satellite passes. So this is referred as off-Nadir viewing capability. So in previous topic I have shown you, I have talked about off-Nadir, how this off-Nadir is going to affect the viewing capability of the sensor, temporal resolution. So when we talk off-Nadir, we say that basically the satellite pass is from, for example, I say just for example that it is from the top of uh, Gujarat to West Bengal. The satellite passes in that particular single range, okay? Or you can say in this particular format from 81° north to 81° south, okay? But uh, for any particular reason, your area of interest is say at 50° or yes, say 54° north is here, so you can change your nadir point. That is nothing but off nadir point. So you can point your sensor to image that area using a particular used by changing the angle. So basically the nadir, I hope you remember what nadir is, but if you don't remember, please go to our previous lecture on orbits in which I have mentioned nadir. So you can see that this is off nadir talk. Off nadir means it is not the path of the satellite, it is neither the path of the sensor, and the sensor point is not to the point below the ground, but it is at actually a particular angle. So it also depends on the off nadir viewing capability of a sensor and satellite. For example, this type of when we talk about off-nozzle capabilities, some of the satellites are or sensors which uses uh, satellite which uses pointable optics, having sampling frequency as high as once in 1 to 3 days are achieved. For example, EGNOS is one of that type of satellite which is used to achieve this type of topic. See, EGNOS has a repeating cycle of 14 days, but it could focus on a certain point uh, as per the requirement of the organization. It could focus on certain point, and because of this, its pointable optics technique, it has a sampling frequency of 1 to 3 days at certain location. Okay. Images of the same area of Earth surface at different period of time shows the variation in the spectral characteristic of different features or areas over time. By that I mean that if you have to focus on a certain area like a geostationary satellite which is used to focus only on a certain area, of course the spatial resolution is very high, very coarse actually but just for example, just for your understanding purpose, we can say that it focuses on the same area of Earth's surface at different period of time, and you can see the variation in this characteristic over time. It shows different features, for example deforestation, or you can say flood, you can say cyclone. This all things can be captured using geostationary satellites. Okay, such multi-temporal data is essential for studies like land use land cover classification, temporal variation in land use and land cover, monitoring of dynamic events like cyclone, flood, volcano, earthquake. Flood studies are also there. You can see here that I will explain. First of all, what do you mean by land use and land cover classification? Is that how different type of land has been used. For example, agricultural land, urban area, building, roads. So a land is how a particular land is used, how a particular land cover is classified. Temporal resolution is very much important when you talk about it. The variation is land unit land cover. That could be explained that, for example, the development of metro project, or the development of road, or the development of building, how much time it take uh, for it, or you can say the urbanization of a certain area. At that time, you can see a variation as you capture the images of same area from 2008 to 2018, or you can capture an image of one particular location, one particular building construction from 2008 to from one to day 200. You can see that how much variation has been occurred. Okay. When we monitor about different events, let me say image which I am showing you, the satellite image before and after the flood event help us to identify the aerial extent of the flood during the progress and recession of the flood event. The Great Flood of 1993, okay, or it is also known as the Great Mississippi and Missouri Rivers Flood of 1993. It occurred from April to October 1993 along the Mississippi and Missouri rivers and their tributaries. The flood was devastating, affecting around 15 billion US dollar of financial loss has been occurred, and was one of the most worst such disaster occurring in US. Here you can clearly see the difference of Landsat images that has been taken during a normal period here, when there was no flood, and during late when the flood has been occurred in the 1993. Comparison of these two images helps us to identify inundated areas during the flood. Okay. Also, But this is one of the example in which you can use it. Now let's say we talk about land use land cover classification. Hmm? So when we say land use land cover classification, temporal variation in spectral signature is valuable. It's very valuable. The spectral signature. Otherwise, you can't classify whether it. How are you going to classify a particular type of land, or whether it is a building, it is a grassland, it is a desert. How? So spectral resolution also important when we talk about classification, along with the temporal resolution. Okay? So temporal variation in the spectral signature is valuable in land use and land cover classification. Comparing multi-temporal images, the presence of feature over time can be identified, and this is widely adopted for classifying various types of crops or vegetation. For example, during growing season, the vegetation characteristic changes continuously. Okay, using multi-temporal images, it is possible to monitor such changes, and thus the crop duration and crop growth stage can be identified, which can be used to classify the crop types. Either they are perennial crops, long crops, or short duration crops. A simple example of Krishna River Basin shows that the Moody's data product, as you can see, from the year 2001 January to November 2001. Okay, I have shown you the different images of Krishna River Basin in different months of 2001. Images of different months of the year help us to differentiate the forest area, perennial crop, and short duration crop. As you can see here, this is the river, and you can clearly see how this red marks are changing continuously along with the river. So I'm not talking about that whether how are you going to classify. This is just an explanation that how in the same year at different months this, but there is changes in these images. Okay, this product has been covered using modest satellite. Again, this is a false color composition using RGB. We have used three colors: red, green, blue, and we have used band 2, band 1, and band 6. Band 2 for red, band 2 is near infrared region, band 1 is has been assigned a green color, and it is red spectral band, invisible spectrum, and band 6 is medium infrared MIR region 1, medium infrared region, and it is assigned as a false color blue. Okay, the concept regarding color composite, I think it has already been explained when we talk about the basic of images. Okay. If not, just let me know, I can cover this topic also. Now, one of the most important thing when we talk about resolution or the resolution of a satellite or sensor is the signal to noise ratio. See, the data recorded on a sensor are composed of the signal, say reflectance, okay, and noise. Noise can be anything. It could be a noise due to some aberration in electronics in the sensor part or data acquisition part. It could be due to moving parts. It could be a defect in the scanning system as they degrade over time. Okay. So in short, we are saying that data recorded on the sensor are composed of the signal and noise. In our case, signal is nothing but reflectance from the object, and noise, it could be from either from electronics or moving parts of the satellite or sensor or anything, and it could be also the defect of the scanning system, because as time passes the sensor gets degraded. If the signal to noise ratio is high, it becomes easy to differentiate the noise from the actual signal. Okay, so the SNR depends on the strength of the signal available and the noise of the system. It should be clearly noticed that if the signal to noise, it has to be high. Increasing the spectral and spatial resolution reduces the energy received and indirectly strengthen the signal. Consequently, What happens if SNR decreases? Also, finer radiometric resolution results in large number of ray levels, and if the difference in the energy level between the two levels is less than the noise, reliability of the recorded gray level diminishes. Of course, that there is always a trade-off between all this type of resolution. In remote sensing, you can say that the energy recorded at sensor depends on the spatial and spectral resolution of the sensor. Okay, but this is a trade-off. Signal to noise ratio has to be good in order to differentiate them. But once it becomes less, it decreases. And sometimes the energy level difference between two level is less than the noise. It becomes hard to classify what is signal, what is. Okay, so we have talked about different type of signal to noise ratio. We have also talked, sorry, not signal, but resolution. We also talked about type of resolution. Those are temp, in this lecture we talked about temporal resolution. Previously we talked about radiometry, then spectral, and we started with spatial resolution. So before ending this topic here, I want to just make it clear that it is not compulsory to have the best of all. We have to make a trade-off in each and every manner to reduces the and to increases our capability. If you have all the best features, of course your output will be best, but in some of the cases, due to some limitation, we have to make a trade-off between this type of resolution. So of course, as I've already informed you, that in remote sensing, the energy recorded at the sensor depends on the spatial and spectral resolution of the sensor. Okay. The radiometric resolution of the sensor varies with the amount of energy received at the sensor. For example, fine spatial resolution requires a small IFOV. Smaller the IFOV, smaller would be the area of the ground resolution cell, and hence less energy is received from that area. When the energy received is less, lesser would be the ability of the sensor to detect the fine energy differences, thereby leading to poor radiometric resolution. Poor radiometric resolution. Now, another trade-off which could be do is that we use the narrow spectral bands to increase the spectral resolution, whereas it reduces the energy received at the sensor in the particular band. A wider band increases the reflected energy. To increase the amount of energy received and hence to improve the radiometric resolution without reducing the spectral resolution, broader the wavelength band can be used. However, this would reduce the spectral resolution of the sensor. Thus, there are a lot of trade-offs has to be done between spatial, spectral, and radiometric resolution. These three types of resolution must be balanced against the desirable capabilities and objectives. Thus, we can say finer spatial, spectral, and radiometric resolution of a system may decrease the SNR to such an extent that the data may not be reliable. Okay. Here we are going to complete our topic on resolution. Hope you have enjoyed this topic, and I hope you have understand what I want to convey through resolution through these topics. Well, we will meet next time with another topic, another lecture. Till then, happy learning. Goodbye. Take care.